There we go. All right. We are now recording and we are going to go over, what is it, direct mapped, set associative, and full associative. I call them memory sorting methods, but it definitely isn't just like cache addressing. Even so, or yeah. All right. So, like to start off, does anyone have specific questions or like would like to start with a different one? Like we don't need to go in order. Like if everyone understands direct or set, or we can go test with one of the others instead to clear up confusion as to how it works. Or would you rather like go through and do like one or two examples on each of these to get a quick understanding of why we sort the data the way we sort it?
I guess just go through each and make sure I want to get a little bit more clear on the specific definitions for each of these terms.
Yeah, I'll try and I'll pull up my draw. Can you guys see when I do this? Like on the
Yes,
screen when I
I can see
annotate? Okay,
when you
good.
edit it.
All right, we'll use that. I like the pencil. Gotta lower the DPI on my gamer mouse for that. All right. So this starts out with direct map. So as she said in class, direct map essentially means it's a scheme where every piece of data that you want to store in your cache has a very specific location. That is, for any given set, there's one set for one range of data. And the reason we say range of data is whenever we pull, like you'll see this later on that this changes depending on which system we're using. But whenever we pull a portion of data, like this is going to start with 48, we can't just say store this, because why would you store us like a single bit of data, right? That doesn't make any sense. Like a single address, there's not much data to be held there. So you store a range. Although now that I remember, I'm pretty sure you just store the range to store the range, just for efficiency's sake. So here, I believe the range is 8. I think it's, what is it, 8 bytes? I think so. Yeah, I think it's byte addressable. So we have 8 bytes here. So what happens here is we start off, and the first thing that's important is this little line right here is the most important thing. So whenever you're running through these problems, you'll be given a bunch of hexadecimal information like this. And it'll be given a scheme, and you have to take this data most likely and sort it and put it where it's got to go, or put it or put the data how it would look after the whole sorting system runs through and is finished. So every single time you do this, you need to get this data, and this information, the tag, the index, the block, and the byte, comes from simply converting the hex number you're given to its binary equivalent. And it breaks apart. You know, these remaining 3 digits are your tag here. These 2 digits are your index, and then the last remaining are your block offset and byte offset. So that's the most important thing. You got to remember to convert to binary in order to understand where to put stuff. So when we're in direct mapped, that means for every set, every position in your table, you're only going to have one range of data. In this instance, the range of data is 8 long, which is going to be 8 like data points long, or yeah, it's going to, yeah, 8 entries long. So what happens here is it goes from what? So we have 0 to F. So in this instance, does it go from 48 to 4F? I'm pretty sure. Should. Yeah, because 484F, that's going to be 8 entries. So we take this entry here, we can break it down to its binary, we go to the tag, and the tag simply selects which set we're putting the data into, or looking for the data. In this instance, technically, whenever we do this, we're always looking for data, hence why this is still a miss, even though this is empty. When it looks for the data, it finds that it's empty, and if it's a miss, it overwrites the data there and just leaves it there. And this goes across all systems. Whenever you start these things up and it's an empty chart, you're just going to start with a bunch of misses, because the system's looking for data, it finds no data, so it counts a miss and then overwrites whatever was there. So to start here, you have your tag, which in binary goes 0, 1, 0, which ends up being technically, oh wait, no, we're talking about the index here. Index tag is going to be put here. The index is what selects your set. So here we have 0, 1, which is 1. So that shoves 4, 8 into the data line. But the thing is, as I said earlier, we end up actually storing a range in all of these. So in this instance, we have M, and this is a range of 8. And why do we say 8? She had a reasoning earlier.
If you look at the byte offset and block offset, those are,
Yes,
that
it's
makes
2,
in
right?
total 3 bits. I don't know exactly how to calculate those off of
I think it's
some of
up
the other
here. She gives
information
us
though.
this. So let's try and figure out why that is the way it is. But you're right about that now I think about it. So the reason we have 3 bits here is we have a block offset of 1 bit and a byte offset of 2 bits. So if we have 32 bytes per word, we have 32 bytes with 1 word for every 4 bytes, 1 block for every 2 words, and 1 set for every 1 block. So direct mapped, the key information you need to know is 1 set per 1 block. And for each of these schemes, there's this key piece of information that you're going to want to memorize because it's extremely useful. And that like key piece of information we're going to address each time for all 3 schemes is like the key piece of information you need to solve all of those clicker questions that were somewhat confusing to people at the last class session. So starting, as he said, as Eric just said, we have block offset and we have byte offset. So let's figure out why. This says we have 32 bytes total, right? And then we have 1 word contains 4 bytes. Cool. 1 block contains 2 words. How do you calculate a block offset? Well, you need to be able to select within a block 1 word or the other word, since it has 2 separate pieces of data, it has 2 words in it. So you need to be able to pick one or the other when you're trying to fetch data. You don't want to fetch the whole sentence, you want to pick one of the words. So what number in binary can represent 2 distinct states? Or how many digits do you need in binary to represent 2 distinct states? You need 1 digit or 1 bit in this instance. So then the next step of information we need to understand here is the byte offset, because the next piece of information is we have this over here. 1 word has 4 bytes in it. So down here we set a block. So that's something I didn't really understand why she did it in this order necessarily. Since it is multiplication, you could do it in any order you'd like. I feel like I'd prefer to do it in like descending order, but it is what it is in terms of like descending order of encompassing. Like, the block holds the words hold the bytes, and the set holds the block holds the words hold the bytes, that kind of thing. But this looks a little jumbly, but oh well. So byte offset, if 1 word contains 4 bytes, how do you represent 4 distinct states in binary? You need 2 bits, therefore 2 bits. So total, this plus this is 3 bits, therefore you can, within a set, which contains 1 block and direct map, you can represent 8 distinct pieces of information within that 1 set. Therefore, you need a range of 8. So in this instance, we have 4, 8. Oh boy, to 4F. Oh boy, F. Yes. 4, 8 to 4F. Don't know why I typed that or wrote that out, because I'm pretty sure on the next slide it shows up. But since we have the range 4, 8 to 4F, now you might ask, why is that the range? It's because you need to pick the range of data that doesn't jump past. You want to pick the least, what is it? How did I explain this in the past? So let's say this was, instead of 4, 8, it was 4, 5. Well, the range you would pick then is going to be 4, 0 to 4, 8, right? No, 4, 0 to 4, 7, I believe would be the proper range there. So you want to pick the range that just goes up to it without, that includes the number you currently have without jumping past. So for example, actually here's a good way. So you see how we have 4s on both of these things within the range. We have M4, 8, 4F. I'm pretty sure regardless, you're not able to overflow past the second digit. So if you had, 4F, right? You wouldn't pick 4F to 5, 7 or 4F to 5, 6. That wouldn't make any sense. You want to pick the range that encompasses the number you have. It doesn't have to be the starting number. It could be within the middle of the range, but it has to encompass the number you are currently working with, and it cannot overflow to the second level. So you need to make sure that these first digits match. You can't overflow to the next level when selecting your range. And to calculate your range, it's based off of the block and the byte offset. which is how many bits. So however many distinct states you have with your combined block and byte offsets. So that's like the method of decomposing a direct mapped piece of information. The most important piece of information to remember with direct map is the fact that one set is equal to one block. And all that really means is as we go down the list of this data, at any given point, there will only ever be one range of data in any given set. There will never be more than one range stored at any given time in any given set. It will always be overwritten if it's a miss. And in this instance, the reason that works out and the reason it works in general is what's awesome about this memory range storage scheme is that eventually, as you store the scheme, some of these pieces of data, in fact, a lot of them, as you can see, either repeat or overlap. So by the end of the scheme, you end up having all of the data stored effectively. It just took a hot minute to figure out where to put it. By the end, all of the data within the range is stored and mapped somewhere, but it takes some time and it's a little bit inefficient, which, you know, we saw we had like a 70% miss rate on the direct mapped. But that's because of that's because it's initializing, starts empty. It's just going to keep missing all the time. So that's the decomposition on how to do something like this. Are there any more specific questions on the direct mapped and like how it like the components of it, or should we move on to just like speed run how it wipes data out and puts new data in?
I'm fine with whatever.
All right, we're gonna try and speed run. Oh, that's a little too fast. So in this instance, as I said at the beginning, if this goes for all mapping schemes, direct, set associative, or full associative, if it's a miss, and if we're working with a full empty, anytime there's a miss, wherever you are, based on your index, like whatever set you're chilling in, if it's a miss, the data that you just, in this case, you're technically putting your range in, the range that you just selected is going there. If it's empty and you miss, it goes right there, as we see here. We're working with 48, it's immediately going to shove it there because it was a miss. And that's how this whole thing works. Every time there's a miss, wherever you are, you shove the data that you're currently holding into where you missed. And that goes for all schemes. So that's that. Now we move on to 0C. So 0C, when you decompose it, is 0001100. So we go to the index. It's on the same set. Well, obviously, 0C does not fall within the range 484F, therefore it's a miss. We're going to overwrite the data. Boom. And that's the range that fits there. In order to hold 0C, you got to go from 08 to 0F. Cool. Overwrote the data. Go over here. Now we're at 48. Oh, isn't that inefficient? We just wiped out 48 with 0C. So we're going to have another miss and put 484F range back in there. And now we're back. And we keep doing this over and over again. We just keep every time that the index bit is the same, we're going to keep going to that spot. And every time that there's data there that doesn't hit it, doesn't get us with a hit. And by the way, the only way you get a hit is if the tag bits are the same. It doesn't have to be the same set of data. The tag bit will simply show, like if you had right here with this first one, if you had 48 mapped to index location 1, set 1, and we were followed by 49, 4A, and so on, we'd be set. Yeah, no pun intended. We'd be good simply because the best part about this scheme, or this in general, is that we're mapping ranges. As long as the memory or the data that you're looking for falls within the range that is mapped to that location, you're good, and that counts as a hit. And we'll see that soon enough, I think, because 2022 should be a map and then a hit. So it'll be a miss then a hit. So it'll put it here. So now we put 20 here, which is the range 20 to 27. Obviously, 22 and 24 both fall within the range 20 to 27. Therefore, these next two systems are going to be a hit, boom, hit, boom. When you have a hit, it doesn't modify the data at all. You just found it. You know, it acts like a pop command because this is technically looking for the data. Oh, where's my data 22? Where's my data 24? Oh, there it is. Take a copy of it. When you're looking for data, you rarely delete it. You're simply taking copies and using it for what it needs to be used for. But when you're missing, you have to overwrite the data. So let's keep going. We're at 80 now. That doesn't fall within range. Delete or overwrite in this instance. We're back to 48. Lucky us though, it's going to actually hit because we already have the range 48 to 4F mapped. Boom, hit, cool. We go over here, we're at 30. 30 has an index that's empty. If every time you go with a data point to an empty index location, it's immediately going to be a miss and write that data in. Now we're at 34. 34 falls within the range 30 to 37. So that's going to be a hit. That is a hit. It says hit here. Now we're at data 26. This is going to be a miss now because we wiped out the data 20 to 27 and replaced it with 80 87. 26 obviously doesn't fall within the range 80 to 87, so miss. And now we rewrite the range 20 to 27. So when it comes to these problems, I think we've done enough of the direct. We'll probably move on to set associative and explain the slight differences between them. I wouldn't say it's slight, actually. It's probably, they're pretty different. Well, set's like the middle ground between direct and full. But what's important with problems like this, I'm not sure test-wise if we would have to do a problem like this, like something like that's exactly like this. You're given this word problem. I don't know if they would, I don't know if she would have the address, like the hex address decomposed already into binary for you. Probably for time concerns, she probably would, but what she probably won't do is this. She probably won't give you the explicit tag, index, block offset, and byte offset. You'll have to calculate that yourself given the information from the problem, which is what those clicker questions are about. So unfortunately, I couldn't find the clicker questions. For obvious reasons, they're not available to us until we've actually used them. Otherwise, we would just have the answers beforehand. Therefore, once we get the clicker questions back, I'm happy to do another session explaining exactly how to do these calculations in more depth. But the trick with these questions is when you're empty, which it probably will start empty, everything's going to be misses until you go back to a range that you filled. Once you filled the range, all you have to do is check, does this hex value fall within the range of the previous hex value that I just mapped? It doesn't, miss. It does, hit. If it hits, you change nothing. If it misses, you simply replace the data that was in that position and move on. And when it comes to actually, once you've done the math, or if we're given this, which would be nice, but if once you've done the calculations and found your tag, index, block offset, byte offset from the binary conversion of the hex data you're given, really the only thing you're focused on from then on out is your index location and your tag. But technically, you don't even have to pay full attention to the tag if you intrinsically understand that if, like going back to 20, 22, 24 example, we missed on 20 because there was nothing mapped to that position yet. But now that it is mapped to the next value, 22 falls within the range 20 to 27, therefore it's a hit. The reason you know that is because the tags will match. But you don't even need to fully comprehend that the tags match in order to know that the number 22 falls within the range 20 to 27. That goes for 24 as well. So while you could, if you wanted to, and this is how the computers do it, they probably use a comparator or something to test that the tag bits match. But we don't need to do such things because we are biological computers that are far more robust in our stupid decision making. So we get to just say, 22 is greater than 20, but less than 27. Therefore, it must be within the range. And that's the way I like to do it because it's a bit faster, in my opinion. Either way. So that's how we do direct map, and that's like the most important pieces of information to understand with regards to how you load these maps with the relevant addresses. Now, I don't know if we'll ever run into problems like this in the long run. I mean, in real life, you probably will run into problems like this. What I'm about to explain is theoretically, if we just had kept having more and more hex addresses and we didn't have enough set space, eventually we would end up losing data or not having map locations for certain bit data. Because here we're lucky because by the end of this, how far down can we go? Let's go all the way through. By the end of this, we have the range 40 to 47 mapped. We have the range 20. Ooh, I can edit this, wild. We have the range 28 to 2F mapped. We have the range 30 to 37 mapped. And we have the range 38 to 3F mapped. Every single piece of data in this list falls somewhere within this range, except for that and that. We actually did lose data here. Actually, never mind. No, it looks like we did just drop data off the face of the earth, huh? So there's just certain stuff that just is not mapped here, huh? That's interesting. Well, that's no fun. Yeah. So I guess we do run into that. So if you lose data, no, not that big a whoop, I guess. Let's move on to set associative. So obviously she doesn't fill these in until a little later. For publicly available, that is. So I'm going to skip past all the explanation part and go to this thing. So the main difference here, so this is called two-way set associative. So here's what you can see. What does two-way set associative mean? One set, two blocks. Nuts. There we go. So this is the other piece of crucial information when it comes to direct mapped or set associative or full associative. The information you need to know is how many sets or how many blocks per set, essentially. In direct mapped, it's one block per one set. In two-way set associative, it is 2 blocks per one set here. So first things first, we're going to want to calculate the range, like how much data we're saving per range. So the first thing we do is go over here. So how much do you need to select a block? Well, there's 2 blocks per set. So in order to represent 2 distinct states, you need 1 bit. Cool. Byte offset. In order to select, there are 2 bytes per word. So in order to represent 2 distinct states, you need 1 bit. So 1 bit, 1 bit. If you have 2 bits total, you can represent, 4 distinct states. Therefore, we have ranges of 4 in this instance. So whenever we're pulling data ranges, we're pulling ranges of 4 for a two-way set associative. So unlike direct mapped, where because of our block and byte offset, we had ranges of 8, in this instance, we have ranges of 4. So we have smaller ranges, but we also have more locations to shove data because this is two-way set associative, 1 set, 2 blocks. Here's a set, but we can store 2 distinct ranges of data in a single set now. Oh boy. Yeah, so we can store 2 distinct ranges of data in a single set without having to kick another piece of data out, which is good. So let's go through and start. So same rule anywhere else. If the full range, if everything in this table is empty, everything in your cache is empty, when you start this thing up and start mapping data, everything's going to be a miss because it's empty until it hits something that you just wrote to. So here, starting at 48 again, it looks like she uses the same numbers each cycle. Starting at 48 again. Also, we have more tag bits here. Tag bits are just simply what's left over after your calculations. So in this instance, since we're only working with 4 distinct sets, we only need 2 bits to represent those 4 distinct states. Block offset, as we said, we have, what is it? We have 2 blocks per set. Therefore, we need 1 bit to represent 2 distinct states. Then we have byte offset. As I said previous, we have to select the byte, 2 bytes for 1 word. Therefore, we need to be able to select which byte we want. So that's also 2 distinct states, 1 bit. So 1 plus 1 plus 2 is 4. 8 total bits is what happens when you have 2 hexadecimal numbers. 8 minus 4 is 4. Therefore, your tag bit is whatever is remaining from calculating these 3 values. Therefore, we have 4 tag bits in this instance. And then in full associative, I think we'll have like 5 tag bits. So the more freedom you're given in terms of where you can put data, the more tag bits you'll need because it becomes more complex to search for the data. So that's just how that ends up working. So starting here, we jump to this location, we just put it in. That's nothing new, we know how to do that. This is a new location, we're just gonna put it in. And I'm pretty sure she said in class she put it over here simply because she can. There's no restriction as to where the system can decide to put. If there's 2 empty blocks in a row, since we have 2 blocks per set, you can simply decide wherever. It doesn't matter where you put it. Within the proper set. You can put it in either block within the proper set. Like this is block 1, this is block 2. That's how this is technically formatted. All right, move on to the next piece of data. So this is going to have a similar tag, and we're going to be lucky here because boom, we're going to have a hit. Nice. So nothing happens. We just took a copy, ran it off to the rest of the system, and dip. Go on over here. We have a miss. But here's the beautiful thing about two-way set associative, or just set associative in general. We have a range that is already mapped to this set. If this were direct mapped, we'd have to kick this out and shove this new data in. But we have an extra block. So we can simply write the data to the second block that's remaining in this same set. Boom. Didn't have to kick any data out. Well, now we're going to have something, huh? 5C does not fall within either of the ranges that we've saved thus far into set 3. Unfortunately, that means we're going to have to kick one of these things out. Another thing that's important, and here's something, I'm going to mention this in a second. So something that's important about this is, just like in direct mapped and just like in full associative, whenever it comes to, and this becomes more important in like set associative and full associative because it's pretty easy in direct map. When you're deciding to kick something out or not, you compare the tag bits and or whether or not the data falls within the range that is saved to that location. In this instance, you're going to have to check the tags of both blocks within the given set to make sure that it's not already there, because otherwise you're kicking data out for no reason because you did find it. So you're going to want to make sure to check both, because if you mess up there, that could be, a big problem later on. So in this instance, now she says evict least. I'm pretty sure, I forget what this exactly means. I don't remember what the LRU means. I'm pretty sure it just means evict the oldest item that has not been used recently. Least recently used or whatever, less recently used, I'm not sure. So it means, let's say I had just used 4C to 4F, but I have not used 0C to 0F. Actually, no, let's flip it. Let's say I just used before this. This didn't actually happen. I don't think it matters here because I don't think we've used either of them. But in this instance, I'm pretty sure we're going to end up evicting 0C to 0F. So here's the order of operations when it comes to evicting in set associative or full associative when you reach a range. I think this is set associative though. Right now we're working with data 5C. It doesn't match with either. So we're going to have to pick one of these to get rid of. Let's look back. Did we have a hit on either of these ranges previously? We're currently operating at, what are we at? No, we're at 5C right now. Wait, did I just delete 5C? I think I did. I did, yeah. Okay, we're currently operating at 5C. It doesn't match either. The last thing that we put in was 4C. It was a miss, and we put it in here. So that was the most recent thing that we put in. This other range, 0C, 0F, was put in previously. Now, we haven't accessed either of these nor gotten a hit out of either of these. That's the first strike. If neither of them have gotten a hit, you have to go down the decision tree and find another piece of information that allows you to decide which one to evict. The next piece of information to consider is which was most recently added to that set. In this instance, 4C's range, 4C to 4F, is the most recently added to the range. Therefore, you evict 0C, 0F. I'm fairly certain. Let's go check that. So let's see. Boom. Yes, that's what happens. If you didn't access either of them, well, whichever one you've accessed more recently is more important. And if you haven't accessed either of them, you wipe the one that was the oldest, unfortunately for them. So now we have 5C, 5.4 written to 0C, 0F's former location. And we move on. 3A, that hits here. It does not match this tag, but we have a space, put it in, no problem. 2.0, it does not match anything, but it's also empty. Put it either place, doesn't matter. They just decide to put it there arbitrarily. Go to 22, we get a hit. Now, if you get a hit on a data point and there is an open location, just remember not to make the mistake to put like a new range, like a double copy into the same set. Like if you get a hit, even if there's an open data range instead associative, it doesn't matter. You got a hit, you just do the copy, you're done, it's done. You finish it like so. Now we're on to 24. 24, traditionally, if we were in direct mapped, there'd be no problems here. If we were in direct mapped, we would have had a hit on the previous data point because the ranges are greater. But in this instance, the range is cut down in half for each storage of a data point. Now we have a range of 4 instead of 8. So this range only goes 20 to 23. We're one off. Gotta need a range of 24. Also, looks like the index is different here because we have a different selection of we have a larger tag in this instance and smaller, what is it? Smaller, I think it was a smaller byte offset. Wait, larger byte offset in the past, in the direct map, I believe. Yeah. Yeah. And because of that, it cuts into our index and it changes the index bit as well of 24, which puts in a new location. Because of that, empty, as we know, shove it in, doesn't matter where. So now we move on, 80, it goes here. If this were direct, we'd have to wipe this out, but it's not. We have an empty slot, put it there, why not? Move on to 48, lucky us, we have that range mapped. We got a hit, we're done there. We're back to 30. Uh-oh, 2023 doesn't hold 30. 8083 doesn't hold 30. That's not gonna do. So we have to go down the decision tree and decide which one's gotta go. We just put the range 8083 in. 2023 is all the way back here. That's where we put in 2023 because this was a hit. So we put in 2023's range back here. But then it got a hit, right? But then we put in 80. But here's the thing. A hit is more important than a write to an empty location. So in this instance, we write or we kick out the 8083 range because the fact that we wrote the data in and then had a hit on the data means it must be more important than the data we simply just wrote in, even though it happened more recently. This got a hit, so this is more important. Never mind, I'm wrong. It's the other way around. Hits don't matter. If we wrote this data more recently, I guess that's primacy. That wins. So let's go back. I got to correct that then. So that is the opposite then. How it works is the thing that you want to consider first is which one came in more recently. Whatever came in more recently matters more. I guess if they came in at the same time or something like that, then it wouldn't matter. Or not. Maybe it just matters whichever came in more recently. That's probably what it is. So simply evict the oldest. Evict the oldest. Yeah, okay, yeah. I got thought of an example that will make this work because the hits do matter in certain scenarios. Let's go back and consider 20 and 3A, hypothetical scenario. We write 3A, it's a miss. We write 20, it's a miss. Then we get a hit on 20. Then we go down the chain somewhere. And then we need to write to the set that holds these. This wouldn't actually happen because these wouldn't overlap. But we have to overwrite this 20. Oh, wait, here. No, let's flip it. Let's say if the 3A were between the 20, let's say we wrote 20, we wrote 3A, and then we got a hit on 22. That hit on 22 counts as a more recent access of that location. So it's not a matter, it's really just whatever location's been accessed most recently is more important, whether that be a write to an empty slot or a hit. And because of that, even though this got a hit, it then had a write into that same set later on. Therefore, 2023 gets wiped because 8083 is younger, so it wins, I suppose. And that's what happens next. Sorry about that. Ooh, move on. So now we go down here, we get a miss because the number 30 doesn't, or 34 doesn't match the range 24, 27. But we got an empty slot, so put it there. Why not? Go to 26. Lucky us, we have that range mapped. We get a hit, we're good. We go to 3E. We don't have that range mapped. Now we need to select which one to get rid of. 3E does not fall within 4C4F, nor does it fall within 5C5F. Therefore, we need to decide which one to kick out. So we got to go back down the list. Where did we write these in? Looks like 5C5F was written in here, where my cursor is, where I highlighted. 5C5F was written in here, and 4C4F was written immediately before it. So technically, right now, 4C4F is older. Let's look through and see if there was anything that would change the rules. Were there any numbers that resulted in a hit on either of these values? Particularly this one. Right now, this one's on the chopping block. The only way it's getting saved is if it becomes real useful real fast, but doesn't look like that's the case. So it looks like 4C4F's getting wiped. And that's exactly what happens. Remember, if you're not useful, they're going to get rid of you. So that's what happens. 3C3F is what takes its place. So now we go on to the next data point. We have 24. We have that range mapped. We're set. That's a hit. 28. Range isn't mapped. We got to decide who's more useful now. So go back through. We have 48. We have 48 to 4B, 38 to 3B. You got to find where those ranges were written. We have a write here, and we have a hit on 48, and we have a hit on 48 here. So right now in the line of succession, we have a 48 all the way up here in terms of usefulness. That's the most recent time it's been accessed. Go over here, and it doesn't have to be the exact same number, 48. Any number that falls within the range that caused activity in that particular set block location counts. So this could very well have been 49 or 4A or even 4B. As long as it's within the range, it counts as a hit or an access. Therefore, it becomes more valuable. So next, we got to check 3A through 3B. When was the last time that was accessed? Well, 38, 38, 38, where was that? Boop, 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 boop. Looks like here. 3A was written to the location, but remember, since we have 2 bits total, that means 4 distinct states. That means 4 for our range. So the range goes from 3.8 to 3B. So 4 3A. So that's the most recent time that it was accessed. Let's look through. 3.0 doesn't fit. 3.4 doesn't fit. 3E supersedes it, doesn't fit. Ooh, unfortunate. Looks like 48 wins the day. And we're going to have to kick out 3.8 3B because it's not as useful. And that's what happens. And we replace it with 2.8 2B. And now we move on to 2C. And 2C goes here, doesn't fall within either range, doesn't fall within either range. We got to find out who's more useful. So who's more useful? Is it 3C 3F or 5C 5F? Well, let's go down the line. Do we see anything? 3C 3F, 3E falls within the range, 3C 3F. So that's a pretty recent access. Does 5C 5F have any competition? 24, 28, 20. Nope. Looks like 5C 5F's getting the boot. It got the boot. That's what happens when you're not useful, it looks like. Let's move on to 40. And 40, we have 2 ranges, 30 to 33, 80 to 83. 40 doesn't fall within either of them, which was the more recent access on our list here. 30, 33, and 8083. Let's go down the line. Here's an 80, but we also have a 30 right here. So unfortunate. Looks like 30 wins today. So 80's getting booted. 80 got booted. And we have 2E, that's the last one. So on 2E, yeah, we have a hit. It falls within the range. 2C, 2F. So we're good. And that completes this range. So you see in this one, we can store more distinct states of data, smaller ranges, but we have the flexibility of being able to store 2 vastly, technically, they could be 2 vastly different ranges that even in direct mapped couldn't have been stored in a single set in this instance, right? Like in direct mapped, there's no way you could get away with storing an 8-bit range in the same set that goes from 3.0 to 4.3, because obviously it takes a lot more than 8 bits to pull that one off. So we have a little more flexibility here, and it's interesting that allows us to do this. But as you can see, the ratios are still looking pretty abysmal, but that's to be expected when you're initializing an empty chart or an empty cache. You're just going to have a disgusting amount of misses because it's empty. And as I said previous, whenever you are working with an empty, chart, an empty cache, you're going to have a lot of misses at the beginning, unless your data was pre-sorted. And if that's the case, why are you even using a write? Like, why are you even mapping stuff if you basically pre-mapped your data? I don't feel like that's useful. So let's go down the line to full associative. Are there any questions on the set associative stuff? Like how the mapping for this one works? Oh, there's chat, isn't there? I don't have that open. Let me look. All right, Francisco 69. What did you mean? So for when the range is important to follow specifically, because that was a while ago. I didn't see the chat at the moment at the time because it wasn't open. If you could message again to qualify that one, I can try and answer. I think I have an idea of what you mean, but I'll need a.
Oh, what I meant by the range is like I think when you do it, you probably want to have the proper steps to know what you're doing,
Like for what, like these ranges?
Yeah,
or
the
stuff up here?
ranges.
Yeah, so like the range is important as in do you want to a refresher on how you calculate it properly for each type of problem, or just like the rules of how to make your ranges, pick your ranges?
I think I understand the ranges. It's just more like I guess how you compute it with the other numbers that's given to you.
Yeah. All right, so we'll go back up to up here. It's easier to see how to do that. So at your original question, so the range is important to follow. It's very important to follow because it's very tempting to simply try and match the numbers. Like looking at this example, like the 20 to 22, right, in this portion, which this is really far back, so it probably got written out somewhere. It did, it got written out over here at some point in history, but even so, looking at this, the range is important to follow to start simply because when you write like the value 20 in, even if you know to write the range, it's tempting to make that mistake and miss out on the fact that this is still a hit. Since the next number doesn't match, it can't be the same, but it still falls within the range that is mapped for any given value. And the thing is, this value doesn't have to be the value that starts the range or ends the range. It can be anywhere in the middle. It just so happens that when we have smaller ranges like 4, it tends that a lot of them will be at the start. But even so that's just how that is. But to calculate the ranges, it all comes down to this line. And I have a prediction that probably when it comes to like the final exam or our homeworks for this stuff, we're going to see a lot of these, like a word problem that just gives us the specifications of our cache, the rules of the cache. And we're going to need to know what those, like how to use those. So the most important data when it comes to this is the rules of your cache and how to interpret the rules of your cache to set the rules or to essentially select the values from your data, because these bits simply come from the hex values you're given. Now, these designations for the bits come from the very important rules. So the first thing, when it comes to calculating your range, the only data you need to look at is the block and the byte offsets summed together. However many bits you need to represent both of them combined is the amount of range. So it's the amount of distinct states you'll represent in a range. So in this instance, we're a two-way set associative. There's 1 bit for block offset, 1 bit for byte offset. Therefore, we need to represent 4 distinct states for our ranges. Therefore, oh yeah, and the counting starts, traditional number system, the counting starts from 0 and then ends at F, since we're working in hex here. So in hex, when you're working two-way set associative with ranges of 4, you're going to end up with the technically, you could have the distinct range of 20, 23, 24, 27, 28, 28, 2B, and then what is it, 2C, 2F? 2C, yeah, 2C, 2F. So those are all the distinct ranges you can represent within a single secondary digit system. I said earlier that with regards to counting on the ranges, you'll never overflow. Like in any given range, if it's less than 16, you'll never overflow past your second digit. Like your second digit will always be the same within your range, and only your first digits will remain this. What will change with respect to whatever you're doing. And I don't think we'll be working with ranges larger than 16. I think that's a little nuts. In real life, maybe, but in this class, no.
Yeah.
So to calculate the byte offset and the block offset specifically, sometimes you're just given them. In this case, you need to look for, to calculate byte offset, you need to look for this piece of information. And to calculate block offset, you need to look for, I think it's this information, set for blocks. Wait. I think it's this information, actually. Now I think about it, I think it's blocks per words. I can confirm this by, I have another tab open with the PDF of this, so I can go look without having to mess up what we're doing right now. So we got to pick which data to calculate our block offset from. Where the hell am I in this information? I am too far up. I'm going to scroll all the way down. Yeah, here's direct mapped. Where's my data for direct mapped? All right. In those direct map examples we were doing, the difference would be it's a range of 8, and it's because the byte offset had 2 bits instead of 1 bit, like we see here. The block offset, however, remained the same at 1 bit. Now, the only difference between the data given to us in a two-way set associative example and a direct map example, actually, there's a couple differences. The difference is, first off, oh boy, I don't even know what that is. The difference is, first off, in the direct, 1 word is equal to 4 bytes as opposed to here where it's equal to 2 bytes. And the other difference is in direct, 1 set's equal to 1 block as opposed to 1 set equal to 2 blocks. But here's the thing, if 1 set's equal to 1 block, then the block offset can't be 1 bit. I mean, it technically could be 1 bit, but it always would be the same number. So that's the trick. Because the block to words. Eric, do you remember by any chance, either of you remember if she said that we use the do we use the set to blocks ratio or do we use the blocks to words ratio for the block offset? Because this is important.
I think for the block offset, I think it makes sense to use the set to block ratio.
That's what I think as well, because the byte
Oh,
offset is explicitly calculated by word to byte, right? So whenever it's an offset, it should be the denominator, is what I'm thinking of the ratios. Because I feel like block to word would be a word offset, right?
Wait. Block to word, yeah, would be the. I think that actually might be the block offset.
That's what, yeah, that's
and
the
the way the
question.
blocks, I think the way the blocks are selected is just by the tag, right? Because you have the two different blocks.
Actually, I don't think,
And
no,
then
no, you don't select. I mean, yeah, no, you're right. You would, in this instance, you would directly select the blocks by tag.
So then you don't, so that block offset is referring to which word in the block.
So it is block to word then.
Yes.
That's what I think. That's what I think that as well. Because the problem is between the direct mapped and the two-way set associative, they both have one block to two word. So technically, you won't see a difference when we scroll down to full associative. There might be a difference. There might not be a difference, but I think I agree with you that the fact that we calculate the block offset based off the block to word ratio. So byte offset's calculated by the word to byte. Yeah, word to byte ratio. And then the block offset's calculated by block to word ratio. So you need to represent two distinct states in both of these systems. Therefore, you use 1 bit. 1 plus 1 is 2. When you have 2 bits, you can represent 4 distinct states. Therefore, our range is 4 in this instance with two-way. Back to direct. The direct examples had a block offset of 1 bit, just like this one, but had a 1 word to 4 byte ratio, which means 2 bits are required. Therefore, 2 plus 1 is 3. Now you have 3 bits, therefore you can represent a distinct number of states equal to 8. Therefore, your range is equal to 8. So that's the long-winded explanation of how you calculate your ranges in any given system. You're looking for your block to word ratio for your block offset and your word to byte ratio for your byte offset. Yeah, that's how it's done. All right. Is that sufficient? All right, gotcha. All right, let's move on to, what is this? Oh, that's for two-way. All right, full associative. I don't want to look at this. That's not what I'm interested in. Wait, this actually might be what I'm interested in. Is this one looks, I'm not sure what it is about it that's different here. Is this an example or is this the actual one we're doing? That is the actual one we're doing, huh? Wait, no. It is, huh? Okay, I'm gonna scroll on down. Nope, way too far. Okay, I'm not sure. So fully associative looks a little bit different, so that's gonna be interesting. Let's scroll down to where we started with. Full associative is right here. So this is the first slide. So we have new information here. Consider a computer with 256 bytes, address equals 8 bits, 32-byte fully associative cache. So we're working with very similar data. So far, 32-byte cache thing is the same data we've had for the other two. The trick here is this time it's a fully associative one, so it operates under different rules. The computer word size is 4 bytes. Our word to byte ratio is 4. Therefore, well, 1/4. Therefore, we need 2 bits to represent the distinct states within that system. Therefore, our byte offset is 2. Each cache block contains 2 words. That means we have 2 words per block. That means you need 1 bit to represent 2 distinct states. Therefore, we have that's the block offset of 1 bit. So we have 3 bits total with our our complete offset calculation or whatever, which means we have a distinct number of states of 8 for our ranges. So our ranges are going to be 8 this time, similar to the direct mapped. So let's go confirm this. So we have 1 word 4 bytes. That's 2 bits. 1 block 2 words. That's 1 bit. 2 plus 1. There we go. And we have 4 blocks in 1 set. total. This is like the full block calculation across the bat. Yeah, across the bat. If you compute this whole calculation, it can give you this. If you go across and multiply 32, divide it by 4, then divide it by 2. Yeah, 32 divided by 8 does in fact equal 4. Lucky me. And she also does the calculations here. She says, in this instance, index in fully associative is not a thing. Because, there's one set and you just shove everything in the set, right? Because there's no index bit, and what I'm about to say she actually does right here, since there's no index bit and we have 3 bits worth of block and byte offset, that means our tag bits are 5 long, or tags are 5 bits long. So you can see here when you want to calculate the number of blocks, you just perform the whole calculation across the board. This isn't just a thing to give you information. It also can calculate the amount of sets or blocks you have in one set. In fully associative, it just means you're just calculating the amount of blocks you have. It's a given you have one set. In fully associative, you always have one set. So now going across, I think the next slide, we're going to be given data that we get to shove in. And I'm pretty sure it's the exact same data we've been working with. Yes, it is. Okay, cool. Knowing that, we can start. So we're starting with 4, 8. Similar to set associative, or similar to all of them, it's empty. You're going to get a miss and you just put it in. And look here, 4, 8 to 4F. That's a range of 8. Good. So that was correct as well. So we get a miss, shoves it in. No problem. So far, so good. No match. And so this is where we get to use a little bit of set associative rules. It's all the same set. We have 4 blocks, so it doesn't match anything. So it's a miss, but you can basically put it wherever the heck you want. So I don't know where it's going to end up. I'm going to take a guess it's going to end up here. Yeah, I was right. All right. So just shoved it in there because it was a miss. Next piece of data, lucky us, it's a hit. So we don't change anything about the cache when it's a hit. Next thing, 4C is a hit, still falls within the range 4, 8 to 4F. We're looking good. 5C, it's a miss, but we have 2 open slots. Shove it into either one. My guess, it appears here. I was right. Also, for anyone thinking I'm cheating by looking at the slides, I am actually legitimately guessing, which I'm impressed that I've got it right twice in a row. Either way, since that's a miss, just shove it in. Not doing anything special yet. Next piece of data, going to be a miss because it doesn't match anything. 3A doesn't fall within any of the ranges we've logged thus far. Therefore, we get to shove it in our last remaining free slot. And now we have a problem because the next piece of data, that being 20, doesn't fall within any of our preceding ranges. So we're going to have to pick one to delete. Now, the rules of deleting data, or kicking it out to replace it with something else, are the same across all of these schemes: direct, set associative, and fully associative. The rules are always the same with that regard. It's always about what was most recently accessed, used, manipulated, whatever you want to say. Whatever was most recently messed around with gets to stay. And whatever is the oldest, or least useful, or least important, gets wiped. So let's look down the line. We're about to go to data point 20. So let's go down the line. The most recent thing that we added was 3A. The next thing we added was 5C. That's over here. Next thing we added was 4C. Well, that was a hit. That wasn't an add, but 4C happened here. Then we had 4.8, which was the right of this position. Well, that was actually a hit as well. 0C is a right here, and 4.8 is the initial right here. The oldest thing we have ends up being 0C, because unfortunately for 0C, it almost saved itself by being, slightly newer than 4.8, but then 4.8 became super useful. So 0C is getting the boot. 0C just so happens to be in the first position, so it gets booted. Well, now it gets booted. All right, it's gone. Replaced with the range 20 to 27. Lucky us, we're gonna have a field day with some hits in a row here. So I'm just gonna scroll past hit, hit. We got 2 hits in a row because 2027 encompasses 22, 24, easy peasy. Now we're on to 80. 80 doesn't fall with any of the preceding ranges we've logged thus far. Uh-oh, got to decide what to boot. So, might have survived the last cycle, but not going to survive this one. 4.8 to 0C is gone already. Oh boy. 4.8 was recently, 4.8 was written here. It was accessed twice, but then 5C was written, 3A was written, 20 was written, 20 got 2 hits. Now we're at 80. 4C was useful, but he fell off the wagon. So he's getting booted. Where's 4C hiding? Goodbye 4C in position 3. Gonzo. Moving on to 48. Well, that's awkward, isn't it? If only 48 lasted a little bit longer, huh? Because now we're gonna have to pick something else to kick out to remap the range 48 to 4F. So let's go back down the list. This is our newest and greatest addition to the team, so that one gets to stay. This has a right and 2 hits in a row, so that's pretty recent. Now we have 3A and 5C, and that means 5C gets the boot. So that means position 4, be no more. And you're gone. All right. And we've written 48 to 4F to position 4, or block 4. There's no real like thing. Technically, these aren't really numbered. It doesn't matter because the computer simply uses the tags and looks everywhere. But until it finds it. But I just like to give the numbers in my head to make it easier. So we just evicted that. Now we go to 30. So where is 30 hiding? Well, unfortunately, it's a miss, as you can tell. 30 doesn't fall within any of these ranges. So we got to pick something to get rid of. So this was just written. This was just written. This is on a roll, still here. And then we have 3A, which is already gone, I believe. Wait, no, 3A is right here. 3A is the oldest, and it doesn't look like it has any accesses, so I think 3A is getting the boot. Yeah, this one, this 2027 range is newer. 80 range newer. 48 was just written. 3A is getting the boot, so 3A, 3F is getting the boot. So position 2 is getting out of here, and it's gone. That's what happens. 34, we have a match hit, nothing happens. Cool. 26, we have a match hit, nothing happens. Cool. 3E, no match. We got to pick what we're getting rid of now. So I think you're starting to see the pattern that the most involved part of this, once you understand the proper method of calculating, like with your given information, calculating your tag. Well, you don't calculate the tag really. Calculating your block and your byte offset and your index. But the index is just from the amount of sets you have. That's what allows you to select between sets. But even so, once you do that, the most involved portion is simply figuring out what data to evict at any given point. And it's all about precedence, essentially. It's all about who's the most useful most recently, right? Computer's got a short memory. So it does not doesn't have really good, computer does not have good relationships with its data. It doesn't really care too much. Short-term memory loss or something like that. Either way, so now we're on to 3E. We have no match. We got to pick something to get rid of. So let's go down the list. This was just a hit. We got a hit here. So we have a hit at position 1. We have a hit at position 2. We have a right of position 2. Then we have 48 back here, which is a right. And then we have a right of 80, 87. And unfortunately, 80's got to take the hit, because it might seem like 2022 24 gets wiped, but remember the ranges count. So 26 falls within that range, therefore it had a hit. So 80's getting out of here. So 80's getting the boot. So position 3 is about to get wiped and replaced with 3E, and that's exactly what happened. Well, 3A to 3F, which encompasses 3E. Regardless, 24 is going to be a hit. It falls within 2027. Cool. But now, well, that was a hit. But now we're on to 28, which barely misses this. So we have to find out what's useless again, or least important recently. So going down the line, 3E was just written. 24 was just a hit. So you're safe and you're safe. No, you're safe. Position 3 and position 2 are safe. Block 3 and block 2, or block 3 and block 1 are safe. No, yeah, block 1 and block 3 are safe. Block 2 and block 4 are up for grabs. So now go down, looking for recent access of 40 and a recent access of 30. Well, these are the rights for both of them. 30 was written slightly more recently, and I don't see any activity on 48 to 4F. So bye-bye position 4, wiped, replaced with 28 to 2F. Now we're moving on to 2C. Lucky us falls within that range. That's a hit. Cool. 40. What does that fall within? Nothing. Got to pick something to get rid of. So go down the line. This is a recent access and a hit on this range. So we're set there. That's safe. So block 4 is safe. Go down 24. That's a safe block. 3E. 3E is right here. It's a recent write. So it's looking like position 2, range 3037, is the oldest. So it's getting wiped. So position 2 will be replaced with 40. And that's what happened, 40 to 47. So now we're on to the last piece of data, 2E. So we have that. That's a hit. It's going to hit in position 428 to 2F. That's what it did. And we're good. You can see here, fully associative's got slightly better stats, right? But this is also mind-numbingly expensive, and I think so, right? I'm pretty sure if you just have space for everything, it gets a little expensive. If you just actually, I'm not sure if this is as much of no. I think direct map's really expensive. Fully associatives is just like weird in the sense that the computer just has to look down the whole list in order to find something. Yeah. I'm not one to speak about the timing efficiencies of these systems. I simply exist to try and make them understandable, I suppose. Either way, are there any questions with the fully associative? Because otherwise we're about finished, because that's all we need to know with regards to these 3 systems and how to calculate the data given. Any other questions or concerns? Yeah. The video will be posted. I will, it's being recorded right now. Yes, it is being recorded right now, right? Yes, I'm fairly certain. Yes, it is. That's good. That'd be an unfortunate time if I made that mistake. But yes, it's being recorded. It'll be posted tonight, probably in like the next hour or 2. So anyone who wishes to rewatch, to review for finals, or I don't know, do better on the next homework whenever that's released for this content, is free to do so, I suppose. So that's the full rundown on direct mapped, set associative, and fully associative. And hopefully it was understandable. So I think that's that. Alrighty then, I will stop the recording then.